Hello friends, welcome back to our Introduction to Fluid Mechanics ENGR 3404. This is our 8th lab. This is the last lab where we're gonna study the total head loss in pipes. It has two parts, if you know. There's major head loss and minor head loss. And that's why we segmented this lab in two parts, lab 8.8a and 8b. So for this lecture, 8a, we're going to cover the energy losses in pipes, which is the major head loss. So let's see what is our learning objective for today. So we're going to investigate the head loss due to friction. So this is our apparatus and this is the pipe. Water will go through and go through this pipe. We're going to study the head loss due to friction, and we're also going to investigate what is the friction factor in the flow of water through this pipe. We're going to run these tests for two different scenarios. One is turbulent flow and one is for laminar flow, and that's why we're going to identify the laminar and turbulent flow based on Reynolds number. That means we also have to find Reynolds number for this test. Finally, once we're done with the test, we're going to investigate the relationship between the friction factor and Reynolds number, and between the head loss and flow rate. So we're going to plot the friction factor against with Reynolds number and head loss with flow rate, and we're gonna study those diagrams. So let's take a brief moment before we show you the demo of the test. The theory that we're going to use. If you remember your Darcy-Weisbach equation for major head loss, which is del H equals to the friction factor and pipe length over pipe diameter, V is your velocity and G is your gravitational acceleration. In this our test, the pipe length, since we are measuring from this point to this point, the head loss, the pipe length would be 0.5 meter from this point where the manometer is connected to where the manometer is connected on the outer portion. And your pipe diameter is 3 millimeter. So and you can find the average velocity if we measure the flow rate, and if you know the cross section from the diameter, you can get the velocity. So let's see how we're going to measure the head loss. If you remember your Bernoulli's equation, if you do the energy balance between a point P1 here and P2, another point at near the outlet, and if we apply the Bernoulli's equation, you will get the pressure head, the dynamic pressure head, and the elevation, change in elevation, and also the friction head loss. This is irreversible loss. So if we assume the diameter of the pipe is constant, it's not changing, so we can assume, which in this case there's no change in diameter, that means there's no change in velocity. And if we neglect the elevation change, we can write del H equals to just change in pressure. And since this is constant, your rho and G, so del H, the change in pressure head, is directly proportional to the change in pressure. And that's what we're going to do using manometer. To take the pressure from here to here, the change will give us the pressure head. So the way we can find the friction factor, if we measure the del H, the pressure head loss, and if we can measure the velocity, and from the Darcy-Weisbach equation, we can find the friction factor. Now, this is the friction factor from experimental. We need to compare the result that we determine with our empirical results. So if you remember your Hagen-Poiseuille equation for laminar flow, which is your Reynolds number should be below 2000, you can just directly find the friction factor using this formula. And when you're doing the test for turbulent flow, you can use the Blasius equation, and in that case the Reynolds number will be between 3,000 to 100,000, and you can use this formula. So what it means is that to find the friction factor using the empirical equation, we need to find the Reynolds number. So this is the one that we're going to find from our test, and this is the values we're going to determine and compare with this value. So Reynolds number, we know this is the equation. It can have two forms. Your rho would be water density, which is 997 or 8 kilogram per meter cube. You have mu, which is the dynamic viscosity at water temperature. That means when we do the test, we also have to take the reading of temperature. And we have to maintain these units to get the dimensionless number, Reynolds number, kinematic viscosity in meter square over second, and d is the diameter, 0.003 meter, and v would be again meter per second. In engineering problem, what we normally do is that use Moody's diagram, where you have friction factor in y-axis and we'll have Reynolds number in x-axis. That's the same thing we're going to do for this lab. After doing the test for a couple of data taken, well, at least 4 or 5 data taken, you're going to plot the friction factor that you received and plot against the Reynolds number. You should receive for laminar flow this trend, and for turbulent flow you should see a linear, because this is the transition. So this is also a way to compare our result with the standards. So let's see. Okay, so before we start our test, let's introduce ourselves with our equipment. Let us introduce ourselves with our setup. This is the setup for measuring the major head loss in pipes, which is also the head loss due to friction. So this is the inlet, and this pipe you see is a smooth pipe, 3 millimeter of diameter. It has a length, because we are measuring pressure from here to there, so this length is half of a meter, and these are to connect the pressure, to measure the pressure at this point, and there is another point here to measure the pressure almost near the outlet of the pipe. We have 2 manometers attached to the system. This one is mercury manometer for high flow rate, so, and this is water manometer for low flow rate. So we can do this test at 2 flow rate. This is the inlet. See, the pipe goes into the tube. If I connect this directly to the pump, it will be high flow rate. And since it's a high flow rate, there will be a lot of pressure, and that's why we need to use a mercury manometer. And when we connect this one to this outlet here, now it is connected with the constant head tank. In this case, what I have to do is that connect this inlet of this tank here, this cylindrical tank, to the pump. The water goes in, fills the tank, and then the water comes out from a constant head, and this way the flow is low, not high. And in that case, we can use the water manometer here. But for both cases in this lab, we will not gonna use either the mercury or the water manometer. We will use a digital manometer. So if you take a closer look of the top part of the constant head tank, the yellow valve is the outlet from the constant head and you see the pipe is connected where the water comes in directly from the pipe through the pipe, fills the water, and then the water goes out through the yellow valve and goes to the pipe that we're testing. This is the bottom section of the system here. This is the overflow from the constant head tank. Whatever water doesn't come through the pipe, the excess water will go out through this port. We put a pipe so that the water doesn't fall on the system. It just fall away from the system. But this here, this is the pipe, if you remember. This is the pipe we're testing for measure head loss. And we have the control valve that we can fully close or fully open. Again, we have just connected another pipe, flexible. It falls down in the tank and we can measure the flow rate. And you also see this pipe is the outlet from the pipe we're testing to the manometer inlet. Since we're not using it, I just put a Hoffman clip to close the water flow. So the water pressure will be going through this pipe, and we'll connect this pipe to our digital manometer. So data collection for major head loss. Remember, our diameter of the pipe was 3 millimeter, and the length from the first manometer point to second is 0.5 meter. We have to take the measurement of the water temperature, assuming that the water temperature will not change throughout the test. So the data collection we have to do for turbulent flow and laminar flow. For each type of flow, we have to collect the volume of water that passes over a certain period of time. That will give us the flow, Q. And from there, we know the cross section. We can find the velocity. And we're going to measure the head loss using the manometer. And you'll see in our cases, we're going to use a direct method of digital manometer. We're going to use instead of the manometer we have over there. And then we're going to calculate the friction factor, and we're going to calculate the Reynolds number. So let's see the test procedure for this lab. So to perform the test, first we're going to run the high flow rate test. For that, we have to take the inlet of our pipe and directly connect to the outlet of the pump. And these are the manometer outlet. So this is the first point. I'm going to connect it to our digital manometer. And this is the outlet from at the end of the pipe. So I'm going to again connect to the other end of our manometer, digital manometer. So we're going to use this manometer instead of these manometers. So you can see there is some air in the pipe. So what we have to do is that we have to run the system for a couple of minutes so that there is no air in the pipe and it is filled with water. So I'm going to turn on the pump. So I'm running the system for about a minute. It is a high flow rate and there is no air in the system. It is filled with water, and water is going out through the pipe here. I have opened the valve a little bit. So what I have to do is that I have to close the valve again so that there is no flow. So I have closed the valve, there is no flow. At this point, I have to balance the digital manometer. So I would say this position is 0. I zeroed it. Now I'm going to open the valve. So now I'm going to open the valve. And there is water flowing. And we can get the head loss. Again, to show you, the pump is running, the water is flowing to the pipe. What I have to do is that close the flow rate. So there is no flow in the pipe. At this position, there is no water flow, and I have to tear, so make this one as a 0. Now I'm going to open the valve, and water is flowing. I think you saw the bubble going through. So now I can take the head loss. The difference is now showing us the head loss between the top part and the bottom part. So the reading is 0.8. If you see the unit, I put the unit water meter. So it is 0.8 meter head loss. Remember, we also have to collect the volume of water flow given a certain time so that we can measure the flow rate. So for that, you see this is the outlet coming through the pipe, right? So and this is my stopwatch. I put it as 0. So I will just start both collecting the water in this beaker here. So let's start. So what I'm doing is collecting water. Instead of collecting water in the tank, I'm collecting in the beaker. So it takes less time. So I'm collecting the water about 15 or 20 seconds. So let's stop. So this is the water collected in 20 seconds. So I can take the reading now. The reading is about 215 milliliter. So this is all we have to do repeatedly for the major head loss, friction loss at high flow rate. We have taken one data set. Now what I have to do is that change the flow rate. So I am increasing the flow rate. So you see the pressure went up from 8 to now 0.9 now. So again, I will take this major head loss, meaning if I increase the flow rate, the loss is more. So at this flow rate, at this major head loss, I have to again collect the water flow given a certain time so that I can measure the flow rate, and from there I can measure the fluid velocity because I know the cross section of the tube here. So we have to repeat this test 4 times and we'll be done with the data collection for the high flow rate. Now we'll move to the low flow rate. So for the low flow rate, I have to turn off the pump. Remember, you have to change the inlet of the water to the outlet of the tank here, constant head tank. Now I need to feed the tank, so this pipe has to go now into the inlet of the pump, and I can run the test. So what will happen, you see water is going into the tank, and the tank is filling up. Once it's filled up, then water will come slowly and it will be low flow rate. Let's see what is inside of the tank looks like. So this is the top view of our tank, constant head tank. How you see the water is coming through the tube here, white tube, and water is filled up the tank. The excessive water is going through the middle pipe here, and the water is coming out from this yellow valve. So the data collection for low flow rate, when the water is coming through the constant head tank into the pipe system here, the procedure is the same as the previous one. I have closed my valve, so there is no water flow through our pipe that we're testing. At this point, I'm gonna make my manometer is 0, and I'm gonna open the valve. What you see over here is the outlet of the constant head tank. The excessive water that is not coming through, it can go through this outlet. So again, it is 0 position. I'm gonna open my valve. So at this position, I have to give a couple of seconds to balance out. So at this position, the head loss is 0.22. Again, what we have to do is that at this position, you have to collect the water of a certain given time. So I have my stopwatch ready, and I have my water outlet. So what I'm going to do is that I'm going to turn both of them on at the same time. So, okay, I started. So I'm collecting the water. I will collect the water up to a certain given time, maybe a minute, or since it's a low flow rate, it will take a while to fill up the small beaker. It can hold up to 250 ml. So let's see how long it takes. So it's already 20 seconds and there's very few water. So I'm keep going. So when it's about like 40 seconds, we'll stop. So a few more seconds to go. So I'll stop at the 40 seconds. So now I can measure, take the reading and the time. This will give us the flow rate, and from there we can find the velocity. The goal is to take a couple of more data, maybe 4 or 5 data points. All you have to do is that you have to regulate the outlet flow. So I can open further. I can open the valve. It will be more flow now. So you see I'm almost 4. So this is the more flow rate, the more head loss, and at this position I can take another data and collect the water volume and given a time, and this way I'm going to conclude the data collection for low flow rate. So we have finished our lab. So on the discussion part, you have to compare the friction coefficient that you find from using the Darcy-Weisbach equation with the empirical equation that we discussed in the theoretical part for laminar and turbulent both flow. And you have to identify the laminar and turbulent flow region by plotting the friction coefficient versus Reynolds number. You see these looks like the same as Moody diagram. For the laminar, you see steep drop. For turbulent, it is kind of slowly dropping. So this is in accordance with your Moody diagram. Again, you have to plot the head loss versus velocity, and you should see a trend line. Now you have to discuss whether these trend lines are expected, whether these trend lines are in agreement with the standards, and that's the part you're going to put into discussion. So that was it for lab 8A. In the next lab, we're going to do the 8B, which is the minor head loss in bends. You know, in pipes, you have long bends, small bends, meter bends, and fittings, you have valves. So there's also head loss on those fittings, and those are called minor head loss. That will be our second part of this lab. Till then, thank you.